Okay, so here we have a 100 kilogram ball, which would probably be pretty big, but we'll say, it's a really small 100 kilogram ball. And we're going to put a particle, just a tiny little particle that has, almost zero mass next to it here. And we want to know how close does it have to be in order for the pull of this 100 kilogram ball to be as strong as the Earth, or the pull of this on this particle to be as strong as the Earth's pull on the particle. So I guess basically, if we have that 100 kilograms there, and we have the Earth here, right? How close does this one have to be? How close does it have to be the 100 kilograms so that these forces would kind of balance out? I guess is another way to sort of look at that there. So. Let's see, the weight of it on Earth. Actually, let's give some subscripts here. So let's say that mass 1 is the mass of our particle. Actually, I'll just say MP is the mass of the particle. That's the particle mass. And then I'll say that, just mass is our 100 kilograms, right? So I get mass, I get M and MP. And we know that the force of the Earth acting on this particle, this is going to be the weight of it, right? So this is just going to be the mass of the particle times gravity, right? That's the weight, which is the force of the Earth pulling on it, right? And so that's equal to, 9.8, mass of the particle, right? Okay. We also know that the gravitational force, Fg, is equal to the gravitational constant times the mass of object 1, mass of object 2, divided by the distance between them squared. Well, we have, object 1 and object 2. That's just going to be our particle, and which I'll call MP, and then the other 100 kilograms is M, right? And so that's the gravitational force. And this is the force of the Earth, so we want them to be equal, right? We're going to find out this R here, so that the force of the Earth and the gravitational force between these two is equal. So I'll just set them equal to each other, and we have here 9.8 MP is equal to G M MP divided by R squared. Okay? Which we have the particle's mass shows up in both of these, actually, so we can cancel this out. So we have here that 9.8 must be G times M divided by R squared. And G is at 6.674 times 10 to the negative 11th, right? We're looking for R. We know G, gravitational constant. We know M. So R is going to be equal to the square root of GM divided by, I'm just going to put little g, 9.8. So our radius here, this is going to be the square root of 6.674 times 10 to the negative 11th. I can't remember if I put a 4 in there on your equation sheet or not. If I didn't, you don't need it. Times the mass of the 100 kilogram particle, so 100, divided by 9.8. And we have this distance here is 2.61 times 10 to the negative 5th meters. So this is, I guess, this radius here would be 26.1 micrometers. So micro is millionth. Or if I wanted to, I guess, yeah, put it in, well, it's very, very small, right? 26 micrometers, or 2.6 times 10 to the negative 5th meters, 2.6 times 10 to the negative 3rd centimeters, right? So it's got to be really, really close, 26 millionths of a meter. And then part B asks, is this, or it's not really part B, but it asks, is this reasonable? You could actually set up this as an experiment. Probably not, because this distance here, remember the distance is from the center of this one to the center of this one. So this would have to be 26 millionths of a meter. And this is really small, but I don't think it's small enough where, its radius is 13 millionths of a meter. It's just going to be too close. I think this particle is going to have to be, inside there. So that's not very reasonable to set up this experiment. And as a fun little extension to this, actually, let's see. You can take here, let's say here's the Earth, right? Actually, let's look at it this way. Here's the Earth, and here is someone standing on top of it, or actually just a ball, whatever, something like this up here. Okay. Then the gravitational force acting on it. Let's say actually this is just 1 meter above, so this is clearly not proportional, but 1 meter above the Earth. And then I have the radius of the Earth is this, right? This would be the radius of the Earth here. Now, let's say I want to find out what the acceleration of this ball is going to be if I just let go. Well, I can use Newton's second law. It says here, the sum of the forces. This would be my y direction down like this. Sum of the forces in the y direction equals mass times acceleration in the y direction, right? So the forces I have acting on is a gravitational force between the two, right? So this is going to be the gravitational force is equal to the mass of a ball. I'll say this is a ball here, times its acceleration in the y direction, right? This gravitational force, this is the gravitational constant, times the mass of the two objects, so this would be the mass of the Earth, times the mass of the ball, divided by the distance between them squared. And let's just say here that this distance, we have the radius of the Earth plus a meter. That's effectively just the radius of the Earth. So let's just say it's the radius of the Earth. So divided by the radius of the Earth squared equals the mass of the ball times the acceleration in the y direction, right? And then again, the mass of the ball cancels out, right? So we have the acceleration of this ball in the y direction towards the Earth, towards the center of the Earth, is a gravitational constant, 6.674 times 10 to the negative 11th, times the mass of the Earth divided by the radius of the Earth squared. So I will leave it to you to plug this in. Look up, I give you the mass of the Earth. This should be in kilograms because the units of this are in kilograms for newtons. And this should be in meters. And take this mass of the Earth in kilograms, radius of the Earth, square it. You can get this from the equation sheet that I give you, or you can just look it up online. Should be pretty. Most places should give it pretty accurately. Look it up in a lot of different textbooks. Look it up in your textbook, and plug this in and see what you get for the acceleration in the y direction. Hopefully, it is something familiar. If it's not, then please talk to me about it.